So in this lecture, we're going to talk about ways to help us interpret effects when we're studying something that we don't know too well, okay? And the idea is simply to compare things with benchmark effects. So to summarize, here's the problem that we're interested in. Here's the real-life data analysis problem. It's hard to interpret an effect or its magnitude because it's hard to interpret an effect or its magnitude because it's a newly studied construct. And the solution I'm going to propose is contrast the effect or the p-value or the effect size or the level of significance with a known construct. So let me give you an example just to kind of frame the discussion. So a friend of mine named Brian Schwartz, he's in environmental health here, wrote a paper called Past Adult Lead Exposures Linked to Neurodegeneration as Measured by Brain MRI. And what they found is an unadjusted effect estimate of negative 1.41 milliliters of brain volume per 1 microgram lead per gram of bone mineral increase, which is a hard thing to interpret. But it's basically saying you lose about 1.14 milliliters of brain volume for every 1 unit increase in lead exposure. He was looking at people who worked in lead manufacturing plants. They are worried that the chronic exposure to lead was causing accelerated brain volume decline beyond that would occur in normal aging. Okay, so how do we interpret this negative 1.14? Okay, we just gave the interpretation, right? It had the units of the problem. However, there is the problem that I still kind of don't know what that means. So here's the idea of putting it into a context with a related phenomenon. So just to remind us, here I'm just looking at one version of the effect. The paper, of course, really drilled down into this problem. So the one version of this effect, the unadjusted effect, was negative 1.41. So a decrease in brain volume as lead exposure increases. But I do know, so I don't understand that effect terribly well because I'm not an expert on lead, let's say, but I do know some things about normal aging. So normal aging over the age of 40 results in about 0.5% of decline in brain volume per year. Okay, so I know it's roughly about that. Maybe that estimate's a little high, but let's say it's roughly about that. So if I take that 0.5% decline in brain volume per year and I look at the average brain volume from Brian's study, then I can figure out that 1.41 decrease is roughly equivalent to about 20% of a year. So basically we're saying this effect that a 1 unit increase in lead exposure, right, results in brain volume loss. That's about the same amount of volume loss that people experience in about 20% of the year over the age of 40. Okay, so to me that's more interpretable because I understand, in this case, because I understand about healthy brain aging because I work in the area. And so what I'm trying to convince you to do is when you're looking at this complicated effect measure, put it into a contrast with something that you're very familiar with. In this case, I'm very familiar with normal healthy aging. I'm not too familiar with lead exposure and its effect on the brain, so I'm going to perform this comparison. And this is a highly powerful technique for bringing and explaining concepts, and it's especially useful when you put these new constructs into the frame of something that everyone in the room is familiar with. So again, this is a technique that is used all the time in epidemiology and public health and biostatistics, and I suggest you try it out in your studies.